ordinary mass of gas is compressed. So I can take one compressed compression process is compressed without friction. Without friction means it becomes a reversible process or a positive motion. From an initial state of 0.1 meter cube, initial volume is 0.3 meter cube, and 0.105 megapascal. That means pressure P1 is 0.105 mega into the power of 6 Newton per meter square to a final state of 0.15 meter cube. V2 is equal to 0.15 meter cube, and pressure P2 it is equal to 0.105 megapascal into the power of 6 Newton per meter square. By looking at this P1 and P2, we can tell it is a constant pressure, and also they mention the pressure remaining constant. Therefore, it will become constant pressure process. Constant pressure process. There is a transfer of 37.6 kilojoules. There is a transfer of 37.6 kilojoules of heat. It is 37.6 into 10 to the power of 3. There is a transfer. Whether it is observed or liberated, I don't know. What is the sign convention of this? This is the system. Work done on the system is negative. Work done by the system is positive. And heat observed is positive. Heat liberated is negative. Now it is a compression process. For a compression process, work done on the system. If work is input, then obviously we convert into other form of energy, that is heat. Therefore, work done on the system is negative. Therefore, work done by the system, by the heat is liberated, that is negative. Since it is a compression, if one form of work is done, obviously heat is liberated. The other heat liberated sign convention is minus. Therefore, this is minus 37.6 kilojoules. How does the internal energy of the gas change? Now, applying first law of thermodynamics. It is a non-cyclic process and a constant pressure process. PV diagram, and it is compression. One where volume decreases. Look at this 0.3 and 0.15. Volume decreases. Area below the curve is work done. It is V2 corresponding volume where it is 1. Area is work done on the system. Therefore, applying first law for a non-cyclic process, Q1 to 2 minus W1 to 2 is equal to U2 minus Q1. Q it is known, W we need to find. So we have to calculate internal energy. U2 minus U1 is how much? Therefore, W for a constant pressure process, W1 to 2 is P2 V2 minus V1. The answer will get joules when you substitute pressure in Newton per meter square, volume in meter cube. Pressure is constant 0.105 into 10 to the power of 6. Volume V2 it is 0.15 and V1 is 0.3. Therefore, W1 to 2 it should get negative. Why? Because it is a compression process. Therefore, minus 15750 joules. Now substitute this here. Q is minus 37.6 into 10 to the power of 3 minus what is minus 15750, and that is equal to U2 minus U1. For U2 minus U1 you get minus 21.85 into 10 to the power of 3 joules. So it's minus 21.85 kilojoules. This is U2 minus U1. Now you got change in internal energy negative. That means U1 is greater than U2. U1 is greater than U2. Therefore, initial internal energy is greater than final internal energy. Therefore, internal energy decreases. internal energy decreases. Next problem. When a system is taken from a state A to state B, shown in figure, that figure I will write it here. This is the figure. This is system A to B, following like this: A, B, B. This is one, and another one is A, this one C state to B, and it is coming back B to A. So following a curve. So this is constant volume. These are straight lines. These are straight lines. This is curve. This is constant pressure, constant volume, constant pressure, constant volume. That is another. Now, when a system is taken from state A to state B, state A to state B, it follows one is this ADB and another one is ACB, during which along path ACB, along path ACB, along path ACB, along path ACB, this is not minus, along path ACB, 84 kilojoules of heat flow into the system. 84, let me write the data. 84 kilojoules of heat flow into the system. Into the system means heat is absorbed. Once again, I will write the system. Sign convention. Work done on the system is negative. Work done by the system is positive. And heat absorbed is positive. Heat liberated is negative. Therefore, heat flow in this ACB, that is heat flow, QACB, is equal to heat flow into the system. Into the system is positive. Therefore, 84 into 10 to the power of 3 joules. And system does, in this ACB, system does 32 kilojoules of work. Therefore, WACB work done by the system is 32 into 10 to the power of 3 joules. These two, they have given a data. Let us go one by one. From these two, if I apply first law of thermodynamics, for which one? ACB process. ACB process, it is an on-site line. Initial state is A, final state is B. An on-site process. I will apply, if I apply QACB minus WACB is equal to final state is UB minus initial state is UA. QACB it is 84 into 10 to the power of 3 minus WACB is positive 32 into 10 to the power of 3. Therefore, you get UB minus UA. Therefore, UB minus UA is same in the internal energy during by following path system ACB, which is 52. Change in internal energy, that is UB minus UA, it is 52 into 10 to the power of 3 joules. UB minus UA is got. Next, let us go one by one determination. Let us go with the A. How much will the heat that flow into the system along path ADB? Now I will consider path ADB. This one ADB along path ADB. How much heat flow into the system? That means I have to calculate the QADB. I have to find QADB. If the work done is 10.5 kilojoules, therefore WADB is what? W work done is 10.5 kilojoules, 10 to the power of 3 joules. So they said how much heat flow into the system. If I consider a system, if heat flow into the system, then obviously the other one will be work. Therefore, heat flow QADP is positive. that is heat supply. Therefore, other word energy transformation is work. That is also positive. They didn't mention work done on the system by the system. They just mentioned work done. By this simple analysis, I can tell it is a positive. Now, once again, I will apply the law of thermodynamics. So QAdP minus WAdP. AdP becomes non-cyclic process. Therefore, final UV minus UA. QAdP is unknown minus WAdP is 10.5 into 10 to the power of 3. UV minus UA I got here 52 into 10 to the power of 3. Therefore, QAdP will get 62.5 into 10 to the power of 3 joules. This is QAdP. Next one, it is question B. When the system is written from B to A, the system is written from B to A, when the system is written from B to A, along the curved path, the work done on the system is 21 kilojoules. That is question B. When the system is written from B to A, work done on the system is 21 kilojoules. That means W B to A, it is on the system minus 21 into 10 to the power of 3 joules. On the system is 21 kilojoules. Now, does the system absorb or liberate heat? That is the question. Now, QBA, I have to find how much is the quantity. Based on that sign, I should tell whether it is absorbed or liberated. Now, applying the first law of thermodynamics, QBA is equal to, applying the first law of thermodynamics, that is B to A, it is the non-cyclic process. Therefore, QBA minus WBA. Finally, initially UA minus UB. So QBA I have to find minus WBA minus of 21 into 10 to the power of 3. And I know UB minus UA is 52, but UVA minus UB is minus 52 into 10 to the power of 3. That is important. UB minus UA is 52 into 10 to the power of 3. Therefore, UA minus UB will become minus 52 into 10 to the power of 3 joules. Therefore, QBA is equal to, we get minus 73 kilojoules. Therefore, based on signal sign, you tell that system liberates 73 kilojoules of heat. Next, C. What is the C? If UA is equal to 0, if UA is 0, UD is 42 kilojoules. UA is 0, UD is 42. Find the heat absorbed in the process AD and DV. Okay? If UA is 0 and UD is 42 kilojoules, find the heat absorbed in the process or heat transfer in the process QAD, how much, and QD. These two we have to find during the process. QAD. We have to find this QAD separately and QDB. Now, let us solve this. ADB to A, or this, the ADB, that is WADB, the network transfer of this ADB can be written as WAD plus WDB. WAD plus WDB. And we know that WADB, this WADB and WDB. AD is a constant pressure process, then WDB is constant volume process. This one, A, WADB is 10.5. kilojoules. That is, this is 10.5 into 10 to the power of 3 is equal to WAD plus WdV. This WdV is constant volume process. This is constant volume process. Therefore, it is for any constant volume process, work done is 0. Therefore, WAD is 10.5 into 10 to the power of 3 joules. We got WAD. Why we calculated WAD? For a AD process, if I write a first law of thermodynamics, QAD minus WAD is equal to UD minus UA. Now QAD is unknown, WAD is 10.5 into 10 to the power of 3 is equal to UD is 1, that is 42 into 10 to the power of 3. UA it is 0. Only unknown term it is QAD. QAD it is 52.5 kilojoules. 52.5 kilojoules. So this is 52.5. Now QdB. How to find QdB? That is QAdB. It is heat transfer in AdB. It is QAD plus QdB. QAdB you already found here. This is QAdB you already found. Now this QAdB it is 62.5 kilojoules, 62.5 into 10 to the power of 3, and QAD you found here, that is 52.5 into 10 to the power of 3. The unknown term here is QdB. Therefore, QdB it is equal to 10 into 10 to the power of 3 joules. Next problem. 0.3 kg of nitrogen gas. Let us write the data. 0.3, that is mass is 0.3, m is equal to 0.3 kg, and the gas here it is nitrogen. At 100 kilopascal, T1 is equal to 100 into 10 to the power of 3 Newton per meter square. And T1 it is 40 degrees Celsius, 40 plus 273, it is 313 Kelvin. The piston is moved compressing. One more term I can get here. It is a compression process, work done on the system. If I consider compression, work done on the system minus, therefore another form of energy will be heat liberated. That also I get negative. The simple analogy that we can verify our answer. Compression. The piston is moved compressing nitrogen until the pressure becomes 1 megapascal. With pressure 1 into 10 to the power of 6 Newton per meter square, and temperature is 160 degrees Celsius, 160 plus 273, that is 433 Kelvin. The work done during the process is 30 kilojoules. Work done during the process is 30 kilojoules. Therefore, what you will write here? It is minus 30 into 10 to the power of 3 joules. Why you written minus? Because it is a compression process. For a compression process, work done on the system is negative. Now apply the first law of thermodynamics. So I don't know which process it is, whether it is constant pressure. Constant pressure is not constant here. So temperature is also not constant. I don't know whether volume is constant or a polytropic process. But simply I'll apply first law of thermodynamics. Q1 to 2 minus W1 to 2 is equal to U2 minus U1. Now Q1 to 2, it is the thing we should find, and W1 to 2. W1 to 2 is V1, and U2 minus U1 we need to find this U2 minus U1. U2 minus U1 it is equal to mCV into T2 minus T1. Internal energy always linked with the specific heat at constant volume. M is 0.3, CV is 0.75 into 10 to the power of 3. Temperature it is 433 minus 330. Therefore, U2 minus U1 you will get 27 into 10 to the power of 3 joules. Therefore, Q122 minus W122 is minus of 30 into 10 to the power of 3 is equal to U127 into 10 to the power of 3. Therefore, Q122 you get minus 3 into 10 to the power of 3 minus 3 into 10 to the power of 3 joules plus minus 3 kilojoules. Therefore, heat is liberated. You can verify by this simple analogy. Work done on the system and heat is liberated in the compression. If one form of work is input, other form will be heat which is liberated. Here enters the compressor at 5 kilopascal. Compressor. Once again, the process is compression. Here enters the 10.5 kilopascal, that is P1 is equal to 25, that is 1 bar Newton per meter square, and temperature 25, that is 298 Kelvin. Having a volume of V1, here it is small volume, I will write telling that it is a specific volume because the unit it is meter cube per kg for a unit mass. For M becomes here, whatever you are calculating, it is for 1 kg. And is compressed to 5 into 10 to the power of 5 kilopascal, that is 5 into 10 to the power of 5 Newton per meter square, and this time it is isothermally. Temperature remains constant, that is T1 is equal to T2. Now determine the work done. Let us calculate the first work done. Let us calculate the first one, that is work done. Work done during the process. For isothermal process, work done is W1 to 2. And W1 to 2 is V1, V1, LAN, V2 by V1. Here V1 is known, V2 is not known. Or else you can write one more thing in terms of pressure. That is P1, V1, LAN, P1 by P2. You know P1, you know V1, and also P1 and P2. Therefore, W1 to 2 is equal to P1. P1 is 10 to the power of 5. V1 is 1.8 and LAN P1 by P2. P1 is 10 to the power of 5. P1 is 5 into 10 to the power of 5. And W1 to 2, you get minus 289.7 into 10 to the power of 3 joules, or else minus 289.7 kilojoules. Negative, you can verify telling that the process is compression. The next one is change in internal energy. Change in internal energy. Change in internal energy U2 minus U1 can be written as MCV T2 minus T1. For isothermal process, T1 is equal to T2. Change in internal energy is 0, or else internal energy remains constant. This is for isothermal process. That we should know. Next, third one, it is heat transfer. After applying the first law of thermodynamics, Q1 to 2 minus W1 to 2 is equal to U2 minus Q1. Q1 to 2 and W1 to 2 is minus of 289.7 into 10 to the power of 3. And U2 minus U1 is 0. Minus into minus plus, therefore it will become Q1 to 2 minus 289.7 into 10 to the power of 3 joules, or minus 289.7 kilojoules. It is a compression process. For a compression process, work done on the system is, if one work is one form of energy, obviously the other form of energy which is going out will be liberated. Work done on the system is negative, heat is liberated, both will be negative. Work done is minus, heat is minus.